Hello everyone, I am Colin Kurz, and this is my report for Lab 1, Constant Velocity. The purpose of this lab was to analyze the motion of an object that was moving at a constant speed without changing direction, also known as a constant velocity. To accomplish this, a video of an object moving at a constant velocity was taken and compared to a computational model of that object moving at the initial velocity of the real object. The result was that the real object slowed down slightly over time, while the computer-modeled object did not. This was because of real-world forces acting upon the real object, causing it to slow down. The fundamental physics principle of this lab was Newton's second law of motion, which states that the net force acting on a moving object is the product of the object's mass and acceleration. In equation form, this law states that net force equals mass times acceleration. According to this law, a system where velocity is constant, and thus acceleration is zero, has no net force acting upon it. Thus, Newton's second law is important to this lab because it shows how an object can keep a constant velocity and shows that an object's velocity will change if net force becomes non-zero. For this lab, the choice of an object to take a video of and analyze was a full can of cherry Pepsi. This object was chosen because it was easy to get to roll in a straight line at a constant speed. A pen with a ruler engraved in it was used as a calibration stick. In Tracker, the x-axis was aligned with the trajectory of the cherry Pepsi in order to ensure that any change in the y direction was minimal. This was needed so that the speed of the cherry Pepsi was relatively equal to its velocity in the x direction, thus eliminating a potential error that the velocity in the x direction and the speed were not equal. In the scope of this lab, the system was the can of cherry Pepsi, and the surroundings were the hardwood floor it was rolling on and the air it was moving through. The importance and impact of the surroundings on the system will be shown later. The computer-modeled prediction of the motion of the object was created by applying the initial velocity of the real object for the entire duration of observation. Newton's second law was applied to update the predicted position of the object at every time interval of 0.033 seconds, equal to a frame in the video of the real object. The resulting predictive graph of x position over time is shown here in Figure 1. The velocity was kept at the constant value of the initial velocity of the real can of cherry Pepsi, as seen in Figure 2. The main difference between the predicted motion of the object and the real motion of the object is that the real object slowed down slightly over time, while the computer-modeled particle did not. This difference is clearly visible in Figure 3. The graph of the computer-modeled particle's position over time is a straight line, while the graph of the real object's position over time has a slight upwards curve as the change in x position becomes less negative, thus its speed is decreasing. The reason why the real object slowed down is because of Newton's second law of motion. In the real world, there are forces acting on all objects, and the most important ones for the sake of this lab are friction and air resistance. These are of particular importance because they impact the movement of the object in the x direction as it rolls along the floor. As seen in Newton's second law, a net force acting upon an object causes its acceleration to change. In this case, the object was moving towards the negative x direction, so the forces of friction and air resistance acted towards the positive x direction to oppose it. This caused the real object to experience positive acceleration, also known as a positive change in velocity. Because the object was moving in the negative x direction, this positive change in velocity caused it to slow down over time. The computer-modeled object did not slow down because no net forces acting upon it were inputted into the model, thus its velocity stayed constant. Some remaining questions are, what if the x-axis was flipped? In this case, the velocity of the object would be towards the positive x direction instead of the negative, and the friction and air resistance forces opposing the motion of the object would likewise switch to being towards the negative x direction rather than the positive. Is it possible to tell how many forces were added together to achieve net zero force to result in net zero force in the observed case? Well, it is possible to tell the forces that were summed to result in the observed net force by analyzing what forces are present on all objects here on Earth. Ideally, forces such as gravity and the normal force acting upon the real object would have resulted in net zero force acting upon it. However, air resistance and friction acting against the motion of the object resulted in the observed net force that caused the object to slow down. In summary, despite efforts to have an object that rolled with a perfect constant velocity, real-world forces cause the observed object to slow down slightly, yielding a less accurate prediction of the motion of the object. Thank you for listening.